The line with the equation y is equal to a is a horizontal asymptote of a function if f of x approaches a as x goes to infinity or x goes to minus infinity. So let's look at a very simple one. F of x is equal to 1 over x. Now let's draw a real quick graph of this. So this graph looks something like this. And we talked about this function when we were looking at vertical asymptotes. So as we learned previously, there is a vertical asymptote at x is equal to 0, which means that this function approaches 0 and as it approaches 0 it goes to infinity, and it does not actually touch x is equal to 0. It's like an invisible wall. But here we can see also, which we did not talk about previously, that there is what also appears to be an asymptote right here. That's because there is also an asymptote at y is equal to 0. Which means that as we get larger and larger x values, this function gets closer and closer to 0, but it does not touch 0. So if we look at this function, and we start putting in larger and larger x values, as this says, there is a horizontal asymptote of a function if the function value approaches whatever value the asymptote's at as x goes to infinity or minus infinity. So we can see here as we put in larger numbers for x, so we can start with 10, this is 1/10, then we can put in 100, then this is 100th, we can put in 1,000, this is 1,000th, we can put in 1,000,000, and this is 1,000,000. So we can see that as we put in larger and larger numbers for x, it's going to get closer and closer to the value of 0. And same thing if we put in net minuses for all these numbers. If we put in negative numbers like -10, -100, -1,000, -1, -1,000,000, it's also going to get closer and closer to 0. But it will never actually become 0. There's no value of x, or of x we can put in here that will cause this to be 0, unless we put in 0, but then we would have an undefined. So we can see that there's a horizontal asymptote at y is equal to 0. So the x-axis is a horizontal asymptote for this function. Now let's look at a different example. But that's the gist of horizontal asymptotes. There's just some value as we put in larger and larger x values that it gets closer and closer and closer to, but does not actually touch it. Just the same idea as vertical asymptotes, but just horizontally. So let's have a look at a function a little bit different, where we won't get an asymptote that is 0. Say we have f of x is equal to 5 plus 2 over x and 1 over x minus 3. And I'm writing it in this way to make it easier to see the horizontal asymptotes. So we know we have a horizontal asymptote if x goes to plus or minus infinity, and as we go to plus or minus infinity, then it gets closer to some value. Then f of x gets closer to some value a. So let's look at this function and ask ourselves, what would happen if x went to infinity? So we can write this. Some people, well, later on in calculus and so on, we're going to the proper notation is f of x as x goes to infinity for the function f plus 2 over x, and then 1 over x minus 3. So we want to know what happens as x goes to infinity. As x goes to infinity for 2 over x. So what happens for 2 over x as x goes to infinity? Well, x is going to become larger and larger, and this value is going to become closer and closer to 0. So first we might start with 2 over 1, and that's just 2, that's fine. Then we go to 2, and then it's 1, and then we go 100, so that's 1 over 5, then, or 1 over 50. So if it was 10, it'd be 1 over 5, and then 1 over 50, and then if we put in 1,000, then it's 1 over 500, and it's going to get smaller and smaller and smaller until it's practically 0. We put in a trillion, 100 trillion, and this 2 is less and less meaningful. So if we say that x goes to infinity, then we're going to say that this value goes to 0. It's going to become smaller and smaller and smaller until this is practically 0. And same thing with this term, 1 over x. It's going to go to 0. So if we put in x is equal to a trillion, this is going to be 2 over a trillion, and it's going to be practically nothing compared to 5, and it's going to be practically nothing compared to minus 3. So we're going to say that this is equal to, as x goes to infinity, to 5 over minus 3, or negative 5/3. So what this means is that there is an asymptote, a horizontal asymptote, at minus 5 over 3. And let's look at one more, and then I'll go over a few tips or a few rules that are very helpful when looking at horizontal asymptotes. I'm going to, well, let me just write it up. So I want to know what the value of this function is as x goes to infinity. Actually, I forgot the x right here. But I want to know what the value of this function is as x goes to infinity. And if we look at this and we say x goes to infinity for the top here, and x goes into infinity for the bottom here, we're going to get infinity over infinity. Because as x goes to infinity, this 1 is going to become insignificant, and this 2 is going to become insignificant. If I put in a million, then 5 times a million, well, this 2 isn't really telling me much. So what I have to do is rearrange this, so I can get a 1 over x or 2 over x, and then we can say that this goes to 0. So I'm going to divide everything out by an x. So this is going to give me 5 plus 2 over x, 1 over x minus 3. And this is the previous problem, and we know that as x goes to infinity, this goes to 0, and this goes to 0. These become practically 0 as we go to infinity. And this is going to give us minus 5 over 3. So I just wanted to show how to rearrange something to get something where we can figure out where the horizontal asymptotes are. But we don't even really need to do this. I recommend doing it this way, but if you want to learn these rules up here, well, I mean, you should probably learn both. Let's look at these rules up here. So if we have some function, a rational function, so a numerator of x and a denominator of x, or it's an x to the n, so some general polynomial, and then another general polynomial in the form of bm x to the n. And our rules are if n is greater than m, so if the numerator, the power of the numerator is greater than the power of the denominator, then there is going to be no asymptote. And if we think about it, that's because if the numerator is higher power, let's say this is x squared, or x to the 5th, plus 1, and then x to the 1st minus 2. X to the 5th is 4 powers greater than x to the first. So it's going to overpower this term. So while it's dividing, it's just going to overpower it. So we're not going to approach any number because this number is exponentially getting larger. And the same thing is going to happen when we have a denominator that's smaller. So if we're dividing two numbers, the numerator is getting larger much faster than the denominator. So it's going to be constantly increasing. So there's not going to be any asymptote. If n is equal to m, like in the example we had below where we had two first order equations, see the largest power here is x to the first and the largest power in the denominator is x to the first as well. If we have two polynomials of the same power, then the asymptote is going to be the leading coefficient divided by the leading coefficient of the numerator divided by the leading coefficient of the denominator. And if we look at this example here, that is because in order to get a situation where we can, so if we're stuck with something like this, we have to divide out by the largest power of x, so we don't get an infinity over infinity. And if we divide out by the largest power of x, that means everything else is going to be divided by an x, and as x goes to infinity, then they're going to cancel out like this. So that's why that happens. That's why only the leading coefficients of the largest power are important when we're looking for horizontal asymptotes. But of course, if you don't want to memorize these rules, you can always just do it this way, where we have some function and we just divide out by x, and then we don't have to memorize anything. We can just say x goes to infinity. What am I left with? This is 5 over minus 3, which is minus 5/3. Or we could have used the rules and said, well, the only ones that are important are 5 and minus 3, because they are the leading coefficients of the largest power. Either way, you can choose. And then our last situation is if the numerator is a smaller power than the denominator, in which case if these were reversed, so if we had an x minus 2 over x to the 5th plus 1, the denominator is going to overpower the numerator. And while in the other case we had no asymptote because it's just going to keep going up and up and up and up like this on it. So if I had some graph, let me just borrow this one. So if this was a situation where we had the numerator was greater than the denominator's power, then it would keep going up and up and up, or down, wherever, if it was positive or minus. But if the denominator has a greater power, then we're going to get a situation where we have like this one right here, 1 over x, where while the denominator has a greater power, it will have an asymptote because we can't get because there's a floor to it. When we're dividing, we're making it smaller and smaller, closer to 0. And what was going to happen is we're going to get closer to 0, but we can't cross 0. You can't divide. When you divide by larger and larger numbers, you just get closer and closer to 0. You don't go further into infinity. While in the case where the numerator is greater, we have no ceiling. We have no ceiling to how far up we can go. But for division, there is a floor to how far down we can go, and that's 0. So that's why when the denominator has a larger power, there is an asymptote, and it will always be y is equal to 0.